www.nanohub.org. You can follow along with this presentation using printed slides from the NanoHub. Visit www.nanohub.org and download the PDF file containing the slides for this presentation. Print them out and turn each page when you hear the following sound. Enjoy the show.
All right, so let's get started. This is lecture 28 on bipolar junction transistor and its design. There will be 3 lectures on this topic, and this is the first one of that series. I could have easily titled this lecture as being this engineer's dilemma between rock and hard place. And that's what you're going to see, that how difficult it is to find right combination of doping so that you can have a great bipolar junction transistor. Now I'll begin by discussing and reminding you one more time that what determines the current gain of a transistor, the variables that determine it, and we'll focus on DC current gain as sort of the parameter to hang various concepts on. So we will use that parameter and then we'll look at it piece by piece to see how to optimize the performance of a junction transistor. Next, we'll talk about this issue about base doping. We'll see that we need in classical homojunction transistor base doping to be as small as possible, but when you try to make it too small, then you run into trouble. Then we'll see that, well, the other option is to go for collector. We'll try to reduce it, but then we'll run into problem again. And then we'll come back for the emitter and try to raise the doping, and then there'll be trouble there again. So you'll see the design of bipolar transistor has this very small space in which you can actually make a transistor. And finally, make some concluding remarks. Now, the considerations today will be mostly on homojunction bipolar transistor. These are silicon, 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 or germanium, germanium, germanium for emitter, base, and collector region. Because of these problems, which we'll cover in this 20-odd slides, modern transistors are no longer homojunction transistor. Heterojunction transistor will allow us to get out of this terrible bind of this doping issues, and that is what most modern bipolar transistors are all about. So we'll get there in next lectures. Let me remind you that the Eber-Small model, in a very simple and elegant form, sort of captures the essence of bipolar operation. We saw that the model essentially looks like this. It is a emitter, base, and collector. So it is drawn here in a common base configuration because base is common between input and output. You can identify this being as an NPN transistor because if you look at the diode on the left hand side between emitter and base, it is looking towards the N side, right? That is how P to N is how the diode should look like. Base is P, emitter is N. And diodes essentially face face away from each other, you can see, because it is NP and then PN between emitter base and base collector. And essentially you can also see that there are 2 other current sources, again essentially facing each other and opposite to the direction of the diode. So very easy to remember. And one thing you will notice that the current source for emitter base depends on the current I sub R, reverse current, between base and collector. Do you see that? And similarly, this is sort of goes crosswise. So alpha F, IF depends on IF on the other junction. And this is reflecting the fact that the current you push through emitter to base, when you forward bias it, the same current flows to the collector side. So that cross coupling is being reflected by these current sources. And we looked into this derived a formula for the emitter current, and that had this diode component which is shown here in red, and also the current source component shown here in blue. look at this IF is by definition IF naught multiplied by the voltage dependent factor. The whole thing is called IF. And correspondingly, IR is the whole voltage dependent thing multiplied by IR naught. That's by definition. And correspondingly, we had an expression for the collector current. You should check the sign, whether the sign look about right, corresponding to the direction of currents that we have shown over there. And the difference between the collector and the emitter current, as you can see from the diagram, Ebers-Moll diagram, would be the base current, right? Because the sum of the three current must be 0. So if you know these two currents, and if there is no current loss, electron cannot be destroyed. It can recombine, that's fine. If it recombines, so one component will go up, another component will go down. But so long electrons are not destroyed, they can recombine, not destroyed, then the sum of the current must be equal to 0, because whatever goes in some form, electron form or hole form, it must come out. And this is the definition, and that's the base current. Now in here I have multiplied with IAE, area of the emitter, and in the bottom area of the collector, A sub C, because the emitter area and the collector area need not be the same. Remember the double diffuse junction? You had these three layers. On the top, emitter was tiny on the top, right? Coming from the top, and the collector was big. So the two areas need not always be the same, but for the simple analysis, we'll assume that they are about the same. Now one plot that is very important and that essentially captures the essence of what a good bipolar junction transistor is given by this following ratio. But before I get there, first of all notice that the collector current depends on base emitter voltage, right? Because I'm forward biasing it, that's how the electrons are getting over the barrier. And also on the base collector bias, because that is on the other side, the reverse bias is pulling the electrons out into the collector. Now, as soon as the VBC is beyond a certain few kT, remember that's a negative voltage. So the term that goes with the exponential of QVBC, that term will go to 0 because it's e to the power minus a large number. So that will go to 0, and this corresponding term will be small. So we'll drop it in the normal active region, not always in the normal active part, because VBC is reverse biased. So we drop that term, small current. So let's focus on the collector current I sub C as a function of VBE. And let's focus on the red line where I show the IC is increasing with VBE. Now do you realize that if I had it in a log plot, log linear plot, then it should be a straight line? You do see that, right? Because if you take a log of IC over A being the area, which I am assuming the same for both emitter and collector, then exponential, whatever is the prefactor, that will become a constant, and Q over KT, that would be the slope. And so that is my first curve. You can see at high current level, the IC current gradually flips over or gradually rolls over. That's the ambipolar type transport, that is the high injection, those type of things. So that is something we are not showing there. So the current will gradually roll off. Now what about the base current? Well, the base current from the previous slide, you can also calculate the base current, and correspondingly the base current will also depend on VBE, because as soon as you forward bias a base emitter junction, electron goes up easily, and the hole also goes to the emitter easily, and so therefore they will have the same dependence on the base emitter voltage. That's very good, and that's what you see in the blue line. If you just look at this expression up to this point, it is not obvious why the blue should be below the red, right? It's just an expression. If you take a log, I can understand why it should go linearly up, but it still doesn't say that, yeah, whether the blue should be higher or lower than the red. But you realize one thing, that if it is a good bipolar transistor and you are taking a signal from the air, right, from the antenna, which is the base current, let's say, and pumping it in your loudspeaker or whatever speaker, in that case, if IC is not bigger than IB, then you are not going to listen to any music. So what I want, and I haven't done that yet, is I have to make sure so that IB is less, orders of magnitude less than IC. And the ratio would be my current gain, that how much amplification do I get as a result of this transistor action. And this we'll call beta. The beta DC is because this is a DC current gain. How good is my amplification? How strong my music comes out when the radio station is really weak. That is the beta DC, the current gain. And it's called a common emitter. I'm sorry, this is a common base current gain. So this is fine, common emitter current gain, because the emitter is common between input and output. Base current is the input and the collector current is the output. Okay. So let's see what that beta DC is. Okay, I can insert those complicated expressions, but you realize that VBC on the numerator, that term, as soon as you have it in a reverse bias, I just dropped it 2 seconds ago, right, in the previous slide, the second term on the numerator, and as a result, now I have a very simple expression. Do you see why? Because on the numerator, I have QVBE divided by KT on the first term. Look at the denominator. Again, I have QVBE divided by KT minus 1, because both are being governed by the base emitter junction. Electron goes easy, holes flow easy also. As a result, the exponential factor will drop out. And of course, the VBC, as I just said, reverse bias, strong negative number, so that number essentially drops out. It simply collects the electrons that is coming from the emitter. So I have this simple expression. You can see there are some diffusion coefficients of electrons and holes floating around. There is this WB and WE, how long the emitter region and the base regions are, and so on and so forth. So we will take this expression apart term by term, and we'll see how to make a great transistor. Now, if you wanted to do a common base configuration, well, that's not difficult either. For example, in that case, you will define another quantity called alpha DC, which is the DC transfer gain, which is the ratio of IC over IE. Look at the top one. Beta is IC over IB, right? IB is a tiny amount of current, but IC over IE, should that number be larger than or smaller than 1? The current is coming from the emitter and flowing in the collector, right? So it could be at most 1 and most likely less than 1 if there is any recombination and other things, less than 1. As a result, you can, and also you can relate it to the beta DC, so you don't have to calculate them separately because of this. Because I know beta DC is IC over IB, IB is IC minus IE, right? That's the difference. And so if I just take a ratio, divide throughout by IE, then IC over IE on the numerator will give me alpha, and correspondingly there will be an alpha on the denominator. And you can see that how beta will be very large, right? If alpha is close to 1, then how large would beta be? Beta will be humongous, because look at the numerator. Because 1 minus alpha and alpha being close to 1, I will get a huge gain. And typical gain of a transistor these days would be on the order of 100 to 1000. So that would be the range of amplification that we are talking about. Okay, so the bottom line of this is no rocket science here, is as soon as you know one quantity alpha, you know the other quantity beta. That's it. So you don't have to calculate them separately. So we'll focus on beta and then do the whole analysis. If I asked you to do about alpha, you will come back and simply put it in this formula and you'll be done. And generally this gain has this various pieces of the same expression I told you about. Now you see, this is, I have plotted beta DC, and you can see this x-axis is about 100. In the bottom, I have it plotted against as a function of IC, which is essentially VBE, because as soon as you increase VBE, IC goes up. So that's your x-axis, and the y-axis is beta. You can see the gain is pretty flat in the middle region. In the very large part, it is rolling off. Why is it rolling off? Because the collector current, because in the high injection part, that's rolling off, but the base current is much smaller. So that doesn't roll off, that doesn't get into the high injection part. So that's why it rolls off on the higher side. In the lower side, because of the base recombination, you should go back and take a look in the previous slide. Because of the base recombination, the base current is very high compared to the collector current. As a result, there is a roll off also in the lower side. So this is our main object of analysis, and from next 4 classes, I am just going to bring this formula over and over again, bring this formula up over and over again, and everything that you have to understand about bipolar, how it operates, all is in here. There are in fact at least 2 Nobel Prizes, maybe even 3 in this formula. So let's start with a given emitter. I have to start with somewhere, so let me assume given emitter thickness, a certain dimension, on the order of, let's say, 0.2 micron, something on the emitter. For a given emitter length, what should I do? In order to get a large gain, I must make the base as short as possible. You can see base is in the numerator. Why is it? Why does it make sense? Because if I make the base smaller, then you can see the gradient of the electron concentration will be higher, right? Because from one side you are injecting from the emitter, on the other side you are collecting it, so the gradient will be higher, current will be higher. That's why you want short base. In 50s, it was even few millimeter. Remember that the triangular waist shape, the first 1947 transistor I showed, they took a blade and cut this gold foil that was going between source and the emitter and the collector, fraction of a millimeter or so. That was what it was in 1950s. Today, if you open up many of these very high performance circuits, then this will be about 200 angstrom. And that is how it has been for at least for last 10 years. Even when I was a student about 15 years ago, when I worked on this, it was about that range. It hasn't changed too much since then. Now let me assume for the time being that the material for the emitter and the base are the same. So therefore, the NIB, which is intrinsic carrier concentration in the base region and intrinsic carrier concentration in the emitter region, what does it depend on, by the way? Depends on the band gap. Do you remember? Ni squared is capital N sub C, N sub V, e to the power Eg over kT. So therefore, we'll assume that both the emitter side and the base side is the same material, same band gap. So I'll drop the Ni squared term. Now, if I assume for a given value of Ne, let's start there. For a given value of emitter doping, in order to get high gain, I must have emitter doping higher than the base doping. You see, this is a central piece. If I don't have the emitter doping higher than the base doping, because this is an exponential factor, 10 to the power 18, 10 to the power 16, so I have a large multiplier here on the doping. Well, it's very difficult to make base very thin. So it's much difficult to control that one. Emitter doping looks like an easy thing to do. I'll just put some dopant in and diffuse it. That will be much nicer. So that is how in 1950s, if you're an engineer at that time, that is how you would think. And we'll start by looking into making base doping as small as possible in order to pump up the beta DC. So you want high gain? Reduce the base doping. That would be your prescription. Unfortunately, so this is what you do. You take the emitter doping, whatever it is, the maximum value you can get at the furnaces at that time, and you will keep the base doping, the green one, lower than that, maybe 2 orders of magnitude, then you get a factor of 100 in gain. The collector one, I have shown it here lower than the base doping, but really, that expression isn't telling me anything about collected doping yet. I will get to that in a little bit later, because from that expression, the NC could be anywhere. We'll get to that in a second. But this would be your recipe, NE larger than NB, in order to amplify or boost a signal from the air to your speaker. So let's see what's wrong in making the base doping small. That's a major problem here. This is what's wrong. The analysis we have done so far is all one-dimensional. We have just assumed that that is vertical cross-section, a one-dimensional cut. That's not really how a transistor operates. There will be many more surprises when you actually do an actual transistor. By the way, do you realize that this double diffuse junction configuration automatically ensures that the emitter will have a higher doping than the base? Because if you had the Na in the base, the green region, if the emitter doping was lower, then you will not have any emitter to begin with, because there is Na already. You put a few Nd, and if Nd is less than Na, then of course that region remains a p-type region. So as soon as you have a n-type region, that means the doping is automatically higher than the green region. Otherwise, Nd is not larger than Na, and you cannot have a transistor. So this configuration automatically ensures that. Now think about it. I have applied a bias VBE between base and emitter, right? Emitter is in the middle. Base is where the red circle is, where the electrons are flowing in. Now, this electron comes in and essentially recombines or goes out through the collector or through the emitter, right? That is the holes coming in from the base contact, they come in and then through the reduced barrier go out through the emitter contact. Now, when they do, you can realize that whatever was the potential difference between the base and emitter contact at the contact point, as the holes are coming down, of course, there will be a voltage drop. And if you keep the base doping low, the green region doping low, that means it has a very high resistance, right? Low doping means low conductivity, high resistance. And so when the hole flows in, there will be a potential drop. And as a result, in the middle of the region, you will have less potential difference than at the edges of the transistor. As a result, there will be a non-uniform turn-on for this transistor characteristics. You can see what I have shown is effective VBE plotted as a function of the horizontal axis within the green region. You can see as the potential, whatever you apply through your battery, a AAA battery or whatever, that's between the black two contacts. As the current is flowing in, then there is gradually potential drop, and so the VBE, the difference between them, is gradually getting smaller. And remember, it's VBE that allows electron to be injected in the base or in the emitter junction. As a result, I have to be very careful about this. Only when my base doping is low, right? Then I'm getting into this trouble. So the beta, now the problem with beta is that it is no longer, you can calculate a ratio, but it is no longer uniform, because current at every point within this, and x is the horizontal axis, depends on a VBE. Well, that depends on the position. How far away is it from the contact? Because it's a low doped base. As a result, what's going to happen is this. Forget about the picture on the left. This is from the book, so that I am just putting it up here so that when you go back home and refer to it, you can refer to that section of the book. But the point is this. As a result of this non-uniform potential drop, there will be more current from the corners, right? Because the VBE is larger there. So that you can see the blue, that current will be, there will be much more current there because it's more forward bias. Do you see the red in the middle? The potential difference is much smaller now compared to what you put in the contact. It has been less forward biased, and as a result, the current is less. And this is called current crowding, because current will sort of crowd near the corners. And most of you can have a huge emitter region, but because of this base resistance issue, low base doping issue, your transistor will sort of look like that it is only conducting at the edges of the emitter. In the middle region, no current. And that's not very good, of course. This will burn the transistor. If you want to pump a certain amount of current, it will burn it. And so therefore, low base doping, you can see, gets us into a lot of trouble. What's the solution? These days, when you look at many of these wireless stations, base stations, when you drive through 65 and others, we see these big towers, right? On the big towers over there, there are these high-powered, about 90 watts, this amplifier that sends out signals. All these cars are getting the radio wave from that antenna. And bipolar transistors over there generally are very high-powered. And those high-powered transistors have emitter and base essentially interdigitated, so that you do not have one big chunk of emitter and one big chunk of collector. It is all interdigitated so that the distance between emitter and base is always minimized, and that way you do not have too much resistance between them. So this is a solution all modern transistors would have because of this base doping issue. So you cannot make it too low. That's what I'm saying. There is more problem if you make the base doping low. So let's say I do that. I reduce the base doping. Now, when I reduce the base doping, do you agree with this statement that I will have a depletion region, base emitter and base to collector? I will have a depletion region. But do you see this WB, what was my original base? That width of the green region. That is not really the base because of this depletion. Because because of this depletion in the base emitter junction, we have done this formula before, right? The amount of this depletion region because of VBE for the bias, whatever region I have. This is not much of a problem. It's a forward bias junction. If anything, it's better compared to zero bias. It's a little smaller. Depleted region is smaller. But what about the collector? Well, on collector, you have applied a huge reverse bias. And as a result, it will be sort of eating up in that region a huge fraction. If you dope it low, you can see, do you see in the formula that the NB is in the numerator? NB is the numerator. It sort of makes sense, right? If you dope it low, it has less charge. It must deplete more in order to provide the charge balance. So the NB is on the denominator, and if you dope it low, it will deplete a huge amount, and at the edge of that depletion region, the carrier concentration will go to zero, right? That's the reverse bias part. As a result, this effective base, W, is actually becoming small, and at large enough bias, it will be completely punched through. It will be completely depleted, and in that case, base has no control. You can see the W on the third figure on the bottom has W equals 0. That means it doesn't have any base. It's no longer a transistor. As a result, low base doping is not a very good idea. Okay, so what are you going to do? First of all, the WB, what I had as a WB in that original formula, the whole formula, I shouldn't be writing as WB. I should be writing as WB prime. Whatever is left after the depletion has eaten away my original metallurgical base region. So WB prime is WB minus the 2 depletion width from the 2 sides. And I said the collector doping, the collector side essentially eats away, collector bias eats away a lot of the region from the base, and that's not a good thing. Now, it's not a good thing because of this following reason. First of all, punch through is you lose transistor action altogether. So that's one problem. But even before that, there are problems. So, by the way, do you see that this gain depends on the voltage? How so? Because generally in the original expression, there is no voltage anywhere. Doping, diffusion coefficient, there's no doping, but no voltage. But now you can see that through the depletion region, the width of the depletion region, well, that depends on the voltage, right? So therefore, your gain will now start depending on the voltage, and that's not very good, and I'll explain in a second. So ideally, this is the rate characteristics you're supposed to have, but experimental data is on the top, and what you see, and what I exaggerate, that in practice, the collector current, even at large VBC, keeps on increasing, and this is because of this depletion issue. So let's see how it works out. By the way, do you see the problem here? First of all, physically, forget about the math. So let's say you're trying to listen to rock and roll or something, big, humongous sounding music. I don't think you hear rock and roll anymore, but let's say, assume that you hear it. Now, if the music is very low, then you have a certain gain. And then if the music is very high, or amplitude is very high, then all on a sudden, you should have a proportional rise in gain. If you don't have a proportional rise in gain, anytime the input is small, then you have a certain gain, let's say 100, factor of 100. Anytime the input is a little higher, then if you don't have 100, then the dynamic range from the inside will be distorted on the outside. Because whatever the singer is doing on the inside, they have a range. But if it is not faithfully reproduced on the outside, if the gain depends on your input signal level, that's not a very good, music isn't going to come out very well, right? As a result, this increase, this difference in IC, increase in IC as a function of VBC. Because remember, VBC is my output voltage. That's what my amplifier, my speaker is. And if that is changing with the input bias, then that's not a very good thing. So we don't want it. So that's the bottom line. Now, how bad it is? How will you know how bad it is? Well, this is how to do it. As I have just told you, that the collector current will depend on WB and the WB prime, and the WB prime depends on VBC, because that's the remaining depletion width. That's what we are talking about. Now, let's see how bad it is. In order to know how bad it is, ideal is if my slope is 0, or that would be my ideal, right? If it is not ideal, then I want to know how bad it is. I can do it by this way. I can say, how is the collector current changing as a function of VBC? That's the derivative, right? And the derivative is the slope. Now, the left-hand side is easy to see. Do you see the right-hand side of the equation, IC divided by VBC plus VA, in the following way? Let's say I draw a line, this blue line going all the way over there. Do you see that at a given point, let's say I have IC, and in the base of that triangle, what is the base of the triangle? VA plus VBC. That's the base of the triangle, and IC over that. Now, for a good transistor, this should be VBC would be small compared to VA, because if it were the red line, what should have been the VA? That should have been infinity, right? Because DIC, that the slope should have been 0, and the only way slope is 0 is VA is equal to infinity. That's the only way it could have been 0. So compared to that, I can always neglect VBC. VBC on the order of maybe a volt or so. So I can drop that. And therefore, in a good transistor, in a reasonably good transistor, I can say IC over VA being the measure of the slope of this bad effect of low doping. And this is called, it's after Jim Early, and this is called an early voltage. The V sub A is called an early voltage. So if somebody says to you, I have a large early voltage, that means he has just designed a transistor which doesn't have this base doping problem. That's what he's trying to tell you. Now let's try to see how to evaluate this formula, because I don't know VA, right? I don't know VA, so how am I going to calculate it? So this is how it works. You see, what I have done in the derivative, I have divided by QNBWB in the first line, and correspondingly, do you see the blue? QNBWB. So top and bottom I have divided it. I haven't done anything. Now, do you realize in the first term, first derivative, I can pull the NB out, QNB out. I have done that. And the QNBWB, what is that, by the way? Q is charge, NB is the doping, right? NB is the doping in the base. WB is the width of the base. So that is the amount of charge. That is the amount of majority carrier charge I have in the base region. So I'll call that Q sub B. All right. Now I know that Q sub B, right? Because I know NB and I know WB from the geometry of the transistor. Now do you see how dQ dVc, what is that? That's the capacitance, because capacitance by definition is a derivative of the charge with respect to the voltage. So that's my capacitance. But why is it dIC over dWb is IC over WB? And why did I get that from here? Now it will take a second. Just take a look. So I have an expression for IC which is inversely proportional to WB. If I take a derivative, what's going to happen? With respect to WB, I will pick up a 1 over WB squared. Now the whole expression divided by WB squared, the first WB, one of the WB I can pull back in IC, and the second WB, well, that's what remains there. So therefore the derivative, you can convince yourself in a second, is indeed that formula. Okay, so I'm getting there. So I combine the two pieces. I have just evaluated the derivative, and if I equate them on the both sides, I get an expression for VA, which is the early voltage. And do you see what early voltage depends on? QNBWB, right? And divided by the capacitance of the collector base junction. This is what it depends on. Now, do you see the problem? What do I want here? VA to be as large as possible, right? That's good, because then I have almost flat characteristics. Now, if I drop NB, that's not a good thing, because if I drop NB, VA will be small. So therefore, my gain will not remain constant, and as a result, I'll be in trouble. So what is the only option do I have here? If I want to keep the base doping low, what is the only option I have? Do something about the capacitance. If I can do something about the capacitance, even with low NB, I still have some hope that the CBC will work out. And that is how the collector doping comes into the story. Now let's talk about the collector doping. So what to do about the collector doping? Here I said that in order to then keep the base doping low, I have to do something about the collector capacitance and keep the early voltage high. And the capacitance, by the way, depends on this. Do you see this? Capacitance between base collector. This is epsilon naught A over D, whatever the depletion width, and the denominator is whatever the depletion width is. So that's what my capacitance should be. This is, by the way, what capacitance is this? This is junction capacitance, majority carrier capacitance. Why did I not write a diffusion capacitance here? Because remember, this is reverse biased junction. So I do not have a diffusion capacitance here. I only have majority carrier junction capacitance. So that's what only thing I wrote. So we'll have to do, if I want large capacitance, then I will have to reduce this depletion. And in order to reduce the depletion, I must increase this depletion. So in order to increase this depletion, then I must reduce the collector doping. That's my only option that I have left. But there's always a but. And this but is that you cannot really do that. You cannot really drop the collector doping arbitrarily low. And that's because of the Kark effect. Now, this requires a little thought. Please follow me, because if you don't, you'll spend a lot of time reading the books and still may not understand it. So it says something easy, but just stay with me for a few minutes. I have only drawn the base and the collector part of it, of the transistor. And I have a, do you see what type of transistor I have? NPN. And I have this collector. You can see the depletion is positive, right? ND is positive. And the green, I have this depletion in the base side. So I have that. Standard transistor. Okay. Now, let's say I start pumping more and more current into this transistor. By the way, so I know this formula, right? That NBXB and NCXC, the depletion on both sides must be the same. I also know VBI minus VBC must be equal to the square of these distances. This you have already done. So there is nothing in here. But notice something that happens when you start pushing a lot of current by forward biasing the emitter base junction. What happens? This is what happens. You see the original green and the ash colored region. That's the equilibrium. But as you start putting more and more current by forward biasing the base emitter junction, your doping, sort of effective doping and effective depletion width changes to the magenta colored region. Why? Because of this. When the electrons are coming, lot of electrons are coming, so it will go like this, the next electron will come, the next electron will come. So the depletion region, which originally didn't have any charge, right? It was completely space charge region, fixed charges. Now there will be electrons flowing, and with a lot of electron, the number could be almost comparable to the background doping. In that case, I cannot neglect that N and P, right? The small n and small p. Electron number I cannot neglect in the Poisson equation. And in that case, my new equation should be NB plus N. You can see the green, the height of that has gone up because it was Na negative, electron coming in negative. So totally NB plus N has gone up. On the collector side, it was a positive, Nd. It was positive, electrons flowing through. Effective charge is a little less than it was before, right? So therefore, you have Nc minus N. And on the other side, you have Nb plus N. Because of this change in the charge, the depletion region will also not remain the same. Xb prime now and Xc prime. You can again do Vb minus Vbc because Vbc is your battery. That has not changed. Vbi is a material dependent thing. That has not changed. So now, when you solve these two pair of equations, what you will see is this. And this is a few minutes, takes a few minutes, go home and do it. The Xc prime, how far it is, how big is the depletion region, that has a complicated expression. But let me just focus on one issue and then I will move on. Is this N? N you can write it as, you see the collector current is Q Vsat N, which is on the left hand side. Why is it? Because it's mostly drift current flowing through the base collector junction, very high field. Do you remember what happens when you have a drift at a very high field? From the first part of the course, do you remember the current comes up and then it saturates? What was the value? About 10 kilovolts per centimeter, right? Do you remember? So here when you apply a volt or a 2 volt on the collector and you have this tiny depletion region, the field is really much higher. So in that case, your current will be simply Q Vsat multiplied by N. So you can relate the carrier concentration N to the collector current Jc. And you can put it in here. That's exactly what I have done. Now comes the punchline. Oh, sorry, I have another slide on here. So first of all, what's going to happen is at low bias, this is going to be your electric field and depletion. As you pump more current, you can see that your base emitter junction is shrinking and the collector junction is increasing, base junction is decreasing, and as you pump more current, the base emitter junction will disappear completely. It will completely disappear because there is no charge. It will be completely disappear, and that's what is called base push out, because base has been pushed out all the way to the collector. Now you have a humongous base, lots of recombination, your transistor is all gone. This is all a consequence of low collector doping. That's why you get into this trouble. And in your book, you will see that a series of curves. In the beginning, you have this base emitter and base collector fields, this constant electric fields on the both sides. And as you pump more and more current, eventually, you see on the base emitter side, the junction has completely disappeared, electron field has completely moved to the other side. Now, at what current does it happen? You can see from that formula what current it will happen. At what current do you think Xc prime will become infinity? Because you don't have any junction anymore. And you can see that will happen when the numerator goes to 0. And when will the numerator go to 0? Well, numerator will go to 0 when the current is so much that it overwhelms the collector doping. Because whatever you had the collector doping, Nd plus, the electrons coming in, it is completely overwhelming the total number of carriers, and as a result, you don't have any junction. And this J sub k is in honor of Kirk, who in 1965-66 first explained this effect. Because of this, people couldn't push the transistor gain to much higher frequency. That I will come later. But this is your problem. You see in here, if you drop Nc too much, what is going to happen? This effect will come at a very low voltage. So you cannot really drop your collector doping too much. So you see the problem. Base doping, you try to reduce it, you get into trouble. Then you say, okay, I'm going to reduce the collector doping. Now you get into trouble here. So you go back and say, well, what can I do? Perhaps high doping in the emitter, maybe because I cannot drop this, maybe I can do something on the emitter side. Unfortunately, you already know the answer. You cannot do that. First of all, because when you have high doping, do you remember band gap narrowing? I talked about these band tail states coming in when you dope very much. So that is one problem that will effectively make this Ni squared much smaller than Nib squared. I have a typo over there, I'll fix it on the numerator. So that's one problem. But the more important problem is, so here it is. So you can see that because at high doping, essentially your gap will be narrowed, your gain will essentially become very small very quickly if you dope it too high. And the other is this tunneling issue. And do you remember this? You must remember this, right? If you try to dope too much, the electrons is not going to go over the barrier and will be controlled by the base barrier. It has an easier path. It will simply tunnel through the emitter to the base and will essentially get out of the base. It will not go to the collector at all, right? Because it can tunnel. It's much easier. And as a result, you will have a horrible transistor. So you can see that yes, emitter should be larger than the base should be larger than the collector, but you have a very narrow space to navigate and to keep your job when the manager says, design me a high frequency transistor. So let me summarize. Now the basic transistor thing that you learn in undergraduate is not too difficult. That is something pretty easy. But when you join a company who is designing a bipolar transistor based circuits, very soon you realize that the teacher and our professor in the undergraduate class didn't really tell you enough of the complicated story. Optimal design is difficult. Now, in general, a rule of thumb is always have to have emitter gain, emitter doping larger than the other two doping. That's generally the case. But the point is that you have this trade-off. Let me quickly summarize them. If you reduce the base doping, what happens? Base series resistance, current crowding, and as a result, non-uniform turn-on. So that's a big problem. And I also have trouble with, if a low base doping, I have trouble with early voltage. My gain is not uniform with respect to the input. So then I go to the collector side, that I need a large depletion width and reduce the collector doping so the depletion mostly proceeds in the collector side. But then I have this problem that as soon as I try to pump up my emitter current so that I have good gain, in that case, the electrons goes through and it overwhelms this depletion region. And very soon the depletion charge is equal to the electrons that is flowing in. And so there is no charge to balance the base charge. Base gets pushed out and you have a base width. You know, you're supposed to have very thin base for good gain. Your effective base now is all the way up to the subcollector region, which is a horrible transistor. So that is the trouble. And finally, if you try to dope too much on the emitter side, tunneling and band gap narrowing, that kills you. So it's a difficult story, but hopefully there are many ways to get out of it. Otherwise, you know, modern technologies wouldn't have really relied on bipolar so much. So we'll get to that in the next 4 lectures. Thank you. Listen, one thing about this, I know these are not easy things, right? There are no good books on this one, unfortunately. There are books where you'll get bits and pieces of it, especially Z's book, SMZ's book. You can take a look. The book, your textbook, that has also. But what I really want you to do, sit down with these slides, maybe with a group of 2 or 3, or come to me. Sit down, and this is, to me, very logical. It will not be logical to you in the beginning. But I'm sure if you sit down and flip slide by slide, you will understand it. If you go for looking for books, hunting for books in the library, well, here I get a little bit, there I get a little bit, you are going to be in trouble because, first of all, symbols are different. People make different approximations, so things are not always consistent. So it's very important that you just sit down with the notes. Don't worry too much about the book yet. First understand the notes, then go back and read the book. You'll be fine. These are not difficult things at all, but do it systematically. Okay.